I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will discuss the example problem for the type breadth first search. See, in the previous lecture, we have briefly discussed about the types of search algorithms. There are two types of search algorithms. All you know that uninformed search algorithms and informed search algorithms, or the another name of the uninformed search algorithm is the blind search algorithms. Informed search, we are calling it as the heuristic algorithms. And uninformed search algorithms, we have seen various types, namely breadth first search, BFS, and DFS, depth first search, and uniform cost search, UCS, iterative deepening depth first search, ID, DFS, bidirectional search, etc. And in the heuristic or informed search, we have seen greedy search, A-star search, and guilt limbing. We'll see one by one in depth. We'll see the example problem. So in this lecture, we will discuss one example problem for BFS. That is, BFS means breadth first search. What do you mean by breadth first search? So the first step involved in this breadth first search is we have to initialize the queue. In this initialization, we have to find out the root node. That root node, we are calling it as the starting node into the queue. And while the queue is not empty, what we should do is we have to repeat the following steps. So first, what we should do is find and add the child nodes. We'll discuss it in the problem. First, we'll see this. Identify the child nodes or successors of the current working node. And for each unvisited child node, we have to mark it as visited, and then add it in the queue. Next, add it into the output sequence. So we have to parallelly do these three things. And then if you are after doing this, we have to dequeue the current node. And dequeue means we have to remove the current working node from the queue. Then we have to update it in the current node. So in this case, what we are going to do in this updating, make the node at the front of the queue, that is the new working node. And we have to go back again to this. So we have to follow again we have to find out from here the step 2. So we'll see the problem. So this is the problem. Here in this, this is the problem description. Here we have, this is the starting node, and these are all the child nodes. This is the parent node, and this node is the first level of the node, and these are all the child nodes. So how we are going to classify means, here we are going in this breadth first search, we are going to find out, that is, we are going to find out the levels, that is depth. That level we are marking it as the L1, L2, and here if you are considering this as the level 3. So as far as this problem is considered, this is the problem description, L3, and this level is the L4. Okay. So in this, how we are going to solve the problem? So we'll see. First, initialization. What is the starting node in this problem? The one is the starting node. This is the parent node. So see the first step. So we have to initialize the queue. In this, we have to find out the root node, that is the starting node in the queue. We have to put it in the queue. So in the queue, we are going to put in the number first node, this one, and we have to visit it. What is the visited? So as far as this node is considered, the visited path is what is the visited thing? The visited thing is only the one. So what is here, what we have to do is, so in this case, so if you are taking in this case, the visited thing is null, empty. So first, I am repeating it. First, we have to find out the parent node, and we have to put it in the queue. This is the initialization of the process. So here levels. So the first level, how many nodes are there? Only one, that is the parent node. Next, we will move on to the second level. So this one, from the one, these 8, 5, 2, 3 nodes are connected. So here first, so in this case, we have to put this one into the queue. What is the second step to be followed? In the second step, we have to dequeue this one. Next, we are moving into the second level. So action, what we are doing it here, the action is we are dequeuing this first node. So once if you are dequeuing, where we have to put it in the output sequence that we are calling it as the visited. And the next NQ, next what are all the things to be in the queue? 8, 5, this 8, 5 and 2. We have to put it in the this NQ 8, 5, 2. Then which one we have to write it? So then, so first, so from this, as far as this case is considered, see here, here it don't have any child, and here it has one child, and it has three children, right? So in this case, first we have to DQ 8, and the action what we have to write it is 8. So once if you are DQing, that should be entered into the visited. That means output sequence we have to write. The remaining things, the 6. So what is the NQ? We have to write it over here for this. Already it is, what are all the things will be in the queue? So 8 alone, in this case, 8 alone we are DQing in the next step. 5 2 will be in the queue. So the 5 2 again remains, it will be same in the queue. So next from this 8, what are all the children for 8? 6, 4, 3. All you have to remember, one, so if you are dequeuing the value from the queue, you have to write, start from this left side, and we have to enter the enqueuing the values from right to, there is a left to right. Here we have to start from the left. So dequeuing should be done in the left side, and while you are writing and you are entering into the values into the queue, you have to write it from here to here, left to right, right? So what are all the values will be available in the queue? 5 2 6 4 3. So we are enqueuing and visitor nodes are 8. What is the next step to be followed? So next we have to DQ 5. Next so this we have entered. This 643 we have already entered. Then we have to move on to the that is depth level. We have to second level we are looking into. This we have seen, and this we have entered, and this we have to see. So there is no child for this 5. So we have to DQ this. So this, once if you are dequeuing, this should be entered into the visited node. Was okay, visited sequence, and enqueuing is none in this case. Why? Because there is no neighbor. So what is the value available in the queue? 2 6. This 2 6 4 3 will be available in the queue. So next, what is the next step to be followed? Next we have to DQ this 2. Once if you are DQing, this value should be put it into the visited node. Then what we have to consider, what is the child for this, what is the neighbor for this 2? 9 is the neighbor for this, so we have to NQ. So we have to this in this case, we have to DQ in the next step, we have to DQ the value 2, and we have to NQ this 6 4 and then 9 in the next step. So this we have done it. What is the next step to be followed? Next we have to DQ 6, right? So next level, next depth we have to move into. So here 6 is the next depth, first value 6 we have to DQ, and then we have to enter into this 6 in the visited, and what we have to write? 10 7. What is the children for this 6 4? Neighbors are 10 and 7 are the neighbors, so we have entered. Then we have to move on to the 4. What is the value for neighbor for 4? There's no neighbor, and for 3 also there's no neighbor. What we have to do? We have to do DQ first 4. We have to put this 4 into the visitor node, that is output sequence. And what is so we have to write NQ is none, there's no neighbor at all. So what is the remaining value available in the queue? 3 9, no, 3 9 10 7. Then we have to look into the, what is the next value? 3. What is the neighbor for this? There is no neighbor, there is no children. So we have to DQ this value, and we have to that is there is no children. We have to DQ into this no visited node. We have to put this 3, and NQ is none, because there's no neighbor at all. So what are all the remaining values are available in the queue? 9 10 7. We have to look into one by one. 9 if you are looking into, this is the first level, so there's no neighbor at all. So that should be DQ'd, and it should be entered into the visitor node. And what is the remaining values available in the queue? 10 and 7. So next we have to look into 10 and 7. So 10 and 7 we have to look into, and there is no neighbor for 10 and 7. So first step is DQ the 10, and we have to put the value in the queue, and there's no neighbor. Again we have to remove, that is dq the value of 7, because there is no children for this, there is no neighbor for this 7. So finally, till the value of q, till it becomes empty, we have to move on. So depth wise we have to consider, one more time I'll repeat it here, we have to separate the nodes into the depth level, depth 1, level 1, level 2, level 3, level 4, etc. And we have to start with the, that is a starting node, and that should be put it into the queue. Then we have to look into the neighboring values, or that we are calling it as the children or child nodes. So till the queue has become empty, we have to move on to the algorithm. So what is the final visited sequences? So for this problem, the final visited sequences, so once the, what is the final BFS, that is breadth first search order 1. So we have to move like this. So 1, 1, 8, 5, 2, and then 6. See here, from 6, 4, 3, then 9. Here there's no neighbor, so we are living under 9. Then we have to come into 6. What is the value? 10 and 7. So this is the order of the nodes resistor. This we are calling it as, another way we are calling it as the output sequence. So we are calling, what we are calling it as the output sequence, or orders of nodes visited. So this is what about the breadth first algorithm. One more time I'll repeat it. First thing, we have to initialize the queue. That initialization, we are going to find out the starting node. So here we have considered that one as the starting node. Some problems they will be given, and then while the queue is not empty, repeat the following steps. So we have to find out each and every children for the parent node. Until the queue is empty, we have to visit the nodes. Okay. So in this way we have to proceed, and we have to find out the output sequence. So the another one more problem. This is the second problem. So in this case, here in this case, they have given this 2 is the starting node. So how we are going to find out? So this is the initial node. So here from this 2, what are all the things are connected here? There is no values are given, the weightages are given. You have to go into the alphabetical order if we are given with A, B, or otherwise ascending order we have to go for. First we have to look into 0, and then we have to look into 1. See, 2, 0. By looking into this directly we can write 0, 1. So next we have to see the, what is that, and also the 6 is also connected here. See here the output sequence, and then we have to see 0. What are all the children for this 0? 3 and 7. 3 and 7 are, so we have written here, right? 3 and 7. Then we have to look into 1. 1, what is the child for this? 4. Then we have to look into 3. So 5. So it is very easy. And in this case, if you have been asking the problem like this, what you have to do is, this is the first step, the order of the table. So we have given, so this is the second step, and here what is the value? The 0, and here we have to write it as 2 comma 0. In this case, you have to write like this. In this previously, see here, 2 comma 0. What is the distance for this? Only 1. How many nodes distance? Only 1. Here only 1 is there. Second one, next, third step if you are considering 1, and we have to write it as 2 comma 2 comma 1, right? 2 comma 1, and the number of nodes visited is 1. And next, the fourth step, if you are taking 6, the value is 6. See here, the value is 6, and in order to move on to the 6, 2 comma 6, how many the distance are? 2 comma, I'm writing it as 2 comma 6, and the distance moved is 1. Next, similarly, in the fifth step, and the 3 value is 3, and then 0 comma 3, the distance moved from this is 2. 0 to 3, if we want to move, see here, from here, that is 0 to 3 here, and then 2 to 0, and here, so the distance moved is 2. Next, in the sixth step, the value is 7, right? And here you have to write it as 0 comma 7, and the distance moved, distance number of edges are 2. So this is very basic problem only. 7, the step, the value is 4. Next, we will be writing 1 comma 4. 1 comma 4 if we want to move it, and the distance moved is here, we have to write it as 2. And in the eighth step, the value is 5. So if you are looking into the problem, we can able to find out 3 comma 5. So if we want to move from the starting node 3 to 5, see here 3 to 5 how it is going. Here 1 step, 2 step, and 3 steps. So what you have to write here? Here the value is so 3. So in this way you have to proceed the. So if you are given with the problem in an indirect way, you have to find out like this. Similarly for this, so here we will write it as, by looking into this, we will write it as 1 to the output nodes 1 to 7. Then 2, we have, what you have to write? 3, 6, and 7 we have to write 8, 10. Next one is, first we have to look into 3, 4, 5. Then we have to write it as 6, there is no children. And for 7 we have to write 8, right? 8 and the 8 and 10 we have already written, right? Then we have to look into this 8 for a value is 9. So in this way you have to proceed the values. We have to find out the output sequence. Hope you have enjoyed, all you have enjoyed this problem. So thank you. And what is the key takeaway on this breadth first search, all of you? Breadth first search is a versatile graph traversal algorithm that explores nodes level by level, ensuring a shortest path solutions. Its applications range from, as I've said, finding shortest path in networks to web crawlers, social network analysis, and path finding in video games. With its simplicity and efficiency, BFS is a fundamental technique in artificial intelligence and computer science. So the remaining the examples we'll see it in the next lecture. Thank you.